This is the second half of the area between two curves lesson. So these are some AP type questions. Some of them are multiple choice, calculator required, calculator not required. Some of them are free response because this is a question that definitely will show up in the free response section. So we will explore all the different types of ways you would see it on the AP test. The first one says, what is the area of the region between the graphs of y equals x squared and y equals negative x from x equals 0 to x equals 2? Notice that one's number 25, which means it is a non-calculator question. So, just for the purpose of this, let me erase all this down here so we have a lot of room to write. First things first, if it's non-calculator, you better make sure that you know what region it's looking at and essentially like what the overall idea is of the area we're trying to find. So if I draw this graph, and I only care about the first quadrant since I'm only looking from x equals 0 to 2, the graph of y equals x squared looks like this. Just draw a couple points. So from 0 to 2, there's my quadratic. And then the line y equals negative x, I guess we do care a little bit about the fourth quadrant as well. Negative x looks like this. And I'll draw that in green. So that's the line y equals negative x. So, excuse me, y equals x squared is the black function. The green function is y equals negative x. I'm integrating from x equals 0, which they both meet at, to x equals 2, so I'll put that in purple. Alright, so there's my region that's bound by all of those functions. And I am looking for this area in here. So, the area is equal to the integral. My lower limit of integration, or the point all the way to the left, is x equals 0. And my upper limit of integration, or the point furthest to the right, would be x equals 2. And then remember, we do top function minus bottom function. So in this case, the top function is the black one, the bottom one is the green one. So the top function is x squared. Top function minus the bottom function, so minus that negative x dx. And that gives me the expression for the length of one rectangle, or the height of one rectangle, and then the integral will add them all up together for me. So, in this case, because it's in the non-calculator section, it is up to us to go ahead and take this integral by hand. The integral of x squared is x cubed over 3. Remember, this turns into a plus. So plus x, the integral of x is x squared over 2. We don't need the constant of integration because we are doing a definite integral. So I'm just going to use the fundamental theorem of calculus. If I plug in 2, I get 2 cubed over 3, which is 8/3. Plus 2 squared over 2, which would be 4 over 2. And then minus, if I plug in 0 to both of those, I get 0. So it's just 8/3 plus 4/2, which is 8/3 plus 2. If I get a common denominator, that's 8/3 plus 6/3, which is 14/3. Answer choice D. 83 is a calculator required problem. I know it because, number one, it's 83. And remember, we talked about how anything above a 70 is a calculator required problem. Secondly, if you look at all the answer choices, they're all decimal forms. And so typically that's kind of a huge indicator that it's going to be a calculator required problem as well. So let's go ahead and actually graph these, because in number 25 it was easy to graph x squared and negative x, but I'm not exactly sure what the graph of that cubic function looks like, so I don't really want to do it by hand. So take a minute and put in that cubic function for y1 in your calculator. X cubed minus 8x squared plus 18x minus 5. And then for y2, put in that second function, x plus 5. And we're going to graph them. So it doesn't give us any limits of integration yet. And so when I graph them, I'm just going to graph them in a standard viewing window from negative 10 to 10 on the x-axis and negative 10 to 10 on the y-axis. And I'm going to see what that looks like. Once I'm done with that and I have a picture of what it looks like, I'm actually going to re-zoom into the pieces of the graph that I actually want to see. So I'll give you a minute to do that. Graph both of these functions as y1 and y2, and then make it so that you can see a nice picture of the graph and the pieces that are enclosed. When you're ready to check out what mine looks like, then go ahead and unpause your video. So pause it now, do that, unpause it when you're ready to see if yours compares to what mine looks like. Alright, so here's what I have so far. I have, up here is my window, so hopefully you guys found a good viewing window for you. I decided to make my x-axis go from 0 to 6 so I could see all of those pieces of intersection, and then I decided to make my y-axis go from 0 to 12 so I could see all of that. So this is what the graph looks like. If you want to change yours, that's fine. If you're happy with what you have, that's fine as well. So here's what I really care about, because I know this is a cubic function. I know this is going to go down this way forever and ever. This is linear. It's going to go this way. They're never going to intersect again over here. And alternatively over here, the same thing. The cubic function will continue up forever. The linear function will continue that way. And therefore, again, these will not intersect. So really the only two pieces of area that I'm concerned about are these two little, or one little and one large piece of area that we see here. So if I go ahead and shade it, I can see there's one point, here's another point, and those are the two areas I care about. Now, remember that any time that one function crosses over the other one and changes which one's on top, we have to set it up as separate integrals. So this first little area over here will be my first integral, and this area over here will be my second integral. In this first one, I need to determine this intersection point. I need to go into my calculator and figure out what value those intersect at. Same thing here, and same thing over here. Because wherever those intersection points are, those are going to be my limits of integration. Remember, I don't want you to guess. I don't want you to try and get close. I want you to figure out the exact intersection point. So in order to do that, we would go to second calc and then option 5 for intersection and figure out all three of those points. So I will give you a minute right now to do that. I want you to go through into second calc intersect and then figure out the x values that all three of these points are intersecting at. So pause your video and then come back once you figured out those 3 points. Alright, so I figured them out on my calculator. I got that they were intersecting at x equals 1, x equals 2, and x equals 5. Now, in this first area, this smaller area, the first thing we have is our cubic function on top and our linear function on the bottom. And in this second area, we have our linear function on top and our cubic function on the bottom. So when I set up my integrals, I'm going to set them up like this. Let me clear some room up here at the top. Now, I know that I typed in my cubic function as y1 and my linear function as y2. So when I set up the integral for area, my first area, this smaller area right here, is going to be the integral from 1 to 2 of cubic minus linear. So in my case, that's going to be y2 minus y1 dx. Plus, the second area, this larger area over here, is the integral from 2 to 5. And now they need to switch. I have my linear minus my cubic. So in my calculator, it's set up as linear being y2 and the cubic function being y1. Oops, that first one's messed up then. Just kidding. Let me fix that. So this first one, if it's cubic minus linear, should be y1 minus y2. And in the second integral, because it's linear minus cubic, it's y2 minus y1 dx. So if you have yours set up the same way where your cubic function you put as y1 and your linear function you put as y2, then this is the integral you will enter as well. If you flipped yours and you put the linear as y1 and the cubic as y2, you'll just have yours flipped backwards. So do me a favor, pause your video, calculate both of those. I will write the answers up here on the board and then, or up on the screen, and then we'll add them together to see what we get. Alright, so I went ahead and did that, and I got that the first area was 0.583, and the second area was 11.25, which makes sense. This one is much smaller than the second one. And so when I added those together, I got 11.833. Answer choice B. So those were examples of how these problems appear in the multiple choice section, calculator and non-calculator. If it's a non-calculator, like I said, it'll be pretty easy to graph, not too bad. They'll give you the limits of integration, not too much work on your part. If it's in the calculator section, it might be your job to go ahead and graph them and kind of figure out what a picture of it looks like. Make sure you're aware of the bounds that we're working with. Possibly even calculate the bounds by finding the intersection points, etc., etc. This is an example of how these problems appear on the free response section. This is number 1. On the free response section, number 1 and number 2 are calculator required, and then numbers 3, 4, and 5 are all non-calculator. So because this is number 1, it's a calculator required question. So let's get started. It says, let f and g be the functions given by f of x equals e to the x and g of x equals ln of x. Find the area of the region enclosed by the graphs of f and g between x equals 1/2 and x equals 1. Now again, you may or may not be aware of what this graph looks like. If I was going to sketch it really quick, you could use your calculator since this is a calculator allowed question. But if you had a pretty good idea of what it looked like already, e to the x goes through the point 0, 1, 1, e, etc., etc. So it looks like this. So this is the function e to the x. And ln of x goes through the point 1, 0, and then it kind of comes down like this and around like this. So that's the natural log of x. Now, you might notice that these functions don't actually touch each other, ever, because they are inverses. And so when we are calculating the area of the region enclosed, it's not bound by the graphs themselves because the graphs never touch. So that's why they had to give us these other points of limits of integration so that we would know where to start and where to stop and what area we were looking at. So it says to start at x equals 1/2. So the line x equals 1/2 is right about here. And that is this function right here. And last but not least, the other bound is x equals 1. X equals 1 is about right here. So the area that we are looking at is the area inside of these two places right here. That pink area that I just highlighted. So here's how you would need to show your work for this question on the AP test. Again, we do not need to do any of these integrals by hand. They are not expecting that from us. They are simply expecting us to show our work and how we got our problem. And then in addition to that, having the correct answer. Now, the graph that I just drew, technically you do not need to draw. If you can picture what this looks like in your head in order to figure figure out which function is on top and which function is on bottom. Like if you knew that e to the x was the top function and ln of x was the bottom function, you wouldn't need to draw the graph. That's not part of the work. So what I'm about to write now is the work you would have to show for this problem. You would have to write that the area is equal to the integral from the lower limit of 1/2 to the upper limit at 1 of the top function, which is e to the x. Now, I know that e to the x is not that much to write, so if you wanted to write e to the x, go for it. And in this case, it's probably just the same as writing f of x. It doesn't matter. But I'm going to get in the habit of writing f of x because later on, when our equations are not so easy to write, and if you miss one thing, like a plus sign or a minus sign, or you accidentally write a 3 instead of a 2, it's going to mess you all up because they have to mark you wrong if you write the wrong thing. So that's why I would say just call it what its name is. So since e to the x is called f of x, I'm going to call it f of x. So it's top function minus bottom function, f of x minus g of x, dx. That is the work for this problem. If you have that on your paper, you're getting full credit for the work. And then after that, it's just a matter of plugging it into your calculator. So do me a favor. And right now in your calculator, you can either go straight into like typing it into the integral if you wanted to, because e to the x and ln of x are not that difficult to write as equations. Or you could put them in as y1 and y2 if you wanted to and recall them that way. So I'll let you make a decision on which way you would rather do it, but go ahead and evaluate this integral right now. Pause your video, and then when you're done evaluating the integral and you have an answer, go ahead and unpause it and see if you got the right answer. So this is the answer I got when I did the integral of f of x minus g of x, which is e to the x minus ln of x, from 1/2 to 1. I got 1.222 if you truncated the answer, or 1.223 if you rounded the answer. You don't need to put both of them on there. I just put both of them because some of you guys like to round and others of you guys like to truncate. So I just wanted to show you which one you could put. You can't put anything else though. 1.221 doesn't cut it. 1.22 doesn't cut it. 1.224, no. You have to round to 3 decimal places, and you can either cut it off after the third one or round it up if it's able to round up. So that is literally all the work. This, what I've written over here in black, is the only work you would need to show in order to get a correct answer for this problem. You do not need to show the graph. You do not need to do any of the math. This is your setup. Essentially for calculator questions, they just want to know, what did you put into your calculator? If you had just written 1.222 or 1.223, then you would have gotten it marked wrong because that's considered a bald answer. But as long as you write what you typed into your calculator and then put what your calculator told you the answer was, you're good to go. Here's another one. It says, let R be the shaded region bound by the graphs of the square root of x, which, if I'm looking at these functions and trying to identify them, y equals the square root of x is this one. And e to the negative 3x is an exponential decaying function, so I'm guessing it's that one. And the vertical line x equals 1, so that's this one right here. It says, as shown in the figure above, find the area R. We know our upper bound is 1, because that's the furthest point to the right. My lower bound I don't know yet, but if we look over here, this is number 1 in the free response section, which means it's calculator allowed, so I can calculate what this value is in my calculator. I just have to put these two functions in as y1 and y2. So I'll do that in a minute to figure out my lower bound. My top function is the square root function. My bottom function is e to the negative 3x. Now notice that both of these equations are called y. If you want to, and I asked about this and they said it's okay. If you want to, you can change this and say, okay, I don't want this to be called y anymore. I want this to be called f of x or g of x, or even y1 if you want to put y1 and y2. As long as you write on your paper somewhere that you are changing the names of the functions, then they will go and look for where you wrote that. If you didn't write it anywhere, of course, we have a problem because they're not going to give you points for things you made up and didn't tell them about. But the reader will give you points if you write in your integral. So I'm going to write in my integral right now. The area equals the integral from, I'm not sure about my lower limit yet, but my upper limit is 1. And then top function is the square root function. We called that y1. Minus the bottom function is that exponential, that's y2, dx. If you write that as your work, and you have y1 and y2 on your paper, the reader's going to go and look for what you want y1 and y2 to be. So up here, as long as you say, oh, y1 is the square root of x, and y2 is e to the negative 3x, then you're good to go. So here's what I need you to do now. I need you to enter those into your equation, into your calculator as y1 and y2. And then I want you to calculate this intersection point so you guys can figure out what point that is in order to find our lower limit of integration. So do that now and then unpause your video when you're ready to check. Alright, so in my calculator when I found that point of intersection, I got that it was 0.2387 on the x-axis. So that's my lower limit of integration. So down here for my work, I'm going to write 0.2387. Again, this is plenty of work. That's all you need to have for work. So now do me a favor and pause your video one more time and put this into your calculator and see what you get for the answer to this integral and write it right here next to it. When I put this into my calculator, I got 0.443 if you're going to round it, or 0.442 if you're going to truncate it. Make sure you got that same answer. Alright, here is our last problem of today. It says, find the region bound by the graphs of y equals 12 minus x squared. That's an upside down parabola, which is this red function. So let me highlight that. Y equals negative x, which is this green function with a negative slope. And y equals positive 4x, which is the blue function with a positive slope. It says, shade the region you're trying to find. So it says, find the region bound by the graphs of, and it's the region bound by all 3 graphs, which is a pretty large area, if you ask me. So if we look at this region here, there's a bunch of different points of intersection. So we are looking for the area here. That is the area we are trying to find, which is bound by all 3 graphs. Now, notice that it looks like it's cut up into 3 different areas. Like this one over here looks like it's cut up into its own little area bound by red, green, and blue. And then this one up here looks like it's cut up into its own area bound by red, green, and blue. And this one over here, red, green, and blue. However, if you look closely at it, there's lines that cut through the middle, and they actually don't affect the areas. So you can do this an easy way, and you can do this the hard way. The hard way would be if you started over here at this left bound and said that's -6. And then if you said, okay, the red function's on top and the blue function's on bottom, and then all of a sudden when you got to here, at this point, now you're looking at green on top and blue on bottom. So like you could essentially divide this area into 6 pieces if you really wanted to. Let me show you what I mean. So you could divide it into area 1, 2, 3, 4, 5, 6. If you really wanted to, you could divide it like that and have 6 different areas, and you could set up 6 different integrals because you'd have different functions on top and bottom, top and bottom, top and bottom. So here it would be, for example, red on top, blue on bottom, green on top, blue on bottom, red on top, green on bottom, etc., etc. However, you can also divide it into less areas. So let me show you what that looks like. If you ignore the lines that cut through the middle of the shape, you can really just divide it into 2 areas. This black one over here on the left, and this yellow one over here on the right. Because if you ignore that line that cuts through it, essentially in this black area, that red function is on top the entire time, and this blue function is on the bottom the entire time. And the green one superficially cuts it in half, but it doesn't affect which one's on top and bottom. And then over here in the yellow region, this blue function superficially cuts it in half, but again, the red's on top the whole time and the green's on the bottom. So this is much easier to do, and we only need to set up 2 integrals rather than 6 integrals. So for the black region, my lower bound is 6, all the way to the left is 6, so the integral would be the integral from -6, -6 all the way to 0, that's where the black region stops. And that's going to be top function minus bottom function. So the red one, which is 12 minus x squared, minus the blue one, which is 4x dx. Plus, the integral for the yellow one would be the integral from 0 to 4, because this point of intersection is 4 right here. Of the top function minus the bottom function would be the red one, which is 12 minus x squared, minus the green one, which is -x dx. So that's your work for it. If we go ahead and put this into our calculator, we can figure out what this is equal to. So go ahead and pause your video. I will figure out the area for this first one, and then the second one separately, and then add them together so you guys can see each piece individually. Alright, so when I put this into my calculator for the first integral, I got an area of 72 units. For the second integral, I got an area of 34.667 units. So when I added the 2 areas together, I got 106.667 units for the area bound by those 3 curves. Alright, and that's the last part for today.